integrate x minus 1 over x squared minus 25 using partial fractions. So let's get the partial fractions decomposition of the integrand. So the top is x minus 1, and the bottom factors into x minus 5 and x plus 5. So that means that the partial fractions decomposition will have a term of the form a over x minus 5 and a term of the form b over x plus 5. Now, if we were to put these two things back on their common denominator of x minus 5 and x plus 5, the numerators would become, let's see, a requires an x plus 5, and b requires an x minus 5. And so this would be the fractions. Since these two fractions are the same, their numerators match. And so we have x minus 1 is equal to a times x plus 5 plus b times x minus 5. Now, all we need to do is substitute in different x values. X equals 5 is a good starting value. 5 minus 1 is 4. We'll have a times 5 plus 5, or 10, but the second term will vanish. And so that means we have 10a is equal to 4, and so we have a is 4/10, or if you'd like, 2/5. So we already know one of the coefficients. We can stick that up here. Now we need another x variable. Let's try x equals minus 5. Minus 5 minus 1 is minus 6. The a term will vanish, and we'll have b times minus 5 minus 5, or minus 10. So we have negative 10b is equal to negative 6, or b is 6/10. That's a 3/5 that we can stick right here. So now we've got the partial fractions decomposition. We know that x minus 1 over x squared minus 25 is the same thing as 2/5 times 1 over x minus 5 plus 3/5 times 1 over x plus 5. Now we can integrate. To integrate x minus 1 over x squared minus 25 dx, that's the same thing as doing the two integrals separately. So we have 2/5 times the integral of 1 over x minus 5 dx plus 3/5 times the integral of 1 over x plus 5 dx, since we've expanded this fraction out. Let's continue this work up here. Now let's prep these two smaller integrals. This is 2/5 times the integral of x minus 5 to the minus 1 dx plus 3/5 the integral of x plus 5 to the minus 1 dx. Now each one of these things is a good candidate for substitution. Focusing on this one first, the substitution u equals x minus 5 is an easy candidate. We'll get us a du equals dx. Since that fits, this will become the integral of u to the minus 1 du, or ln of the absolute value of u. And if we back substitute, we'll have the 2/5 that came along for the ride, the natural logarithm of x minus 5. This should be easy at this point. Working on this green integral, we'll do the same trick. We'll let u be x plus 5, the expression in parentheses. The same derivative argument shows that the differential du is dx, and so we can make the replacements and get the integral of u to the minus 1 du, and once again we get the natural logarithm of the absolute value of u, or a 3/5 the natural logarithm of x plus 5 from the green integral. And since we've solved both problems together, we add them up, throw on a plus c, and we have the general antiderivative.